So in this second video about titrations, we want to go through step by step the titration of a weak acid with a strong base. This is a great diagram from a book by Daniel Harris, and this actually is on the inside cover of the book. And I just think it's very useful. The problem of a weak acid being titrated with a strong base actually brings together many of the things that we've studied. You have the pH on the vertical axis and the volume of added base on the horizontal axis. And before you start adding base, before you start the titration, you just have a weak acid in solution. We've solved that problem many times: acetic acid in water, benzoic acid in water, and many others. So we know how to do that. In this book by Harris, he uses the F for formal concentration. So if you have a 0.1 molar solution of acetic acid, he would say F is equal to 0.1. Okay, and we know how to solve that. It's the square root of the Ka times the formal concentration is X, and X would be the hydronium ion concentration, and we could take the negative log of that and get the pH. Okay. Then look at the equation at the top in yellow. I tried to highlight it. Okay. The acid is HA, and it's being treated with OH minus to produce A minus. As the titration proceeds, HA is being converted to A minus. It starts out essentially all in the HA form. As you know, weak acid just dissociates a little bit. So it's mostly HA. And then you add base, strong base, reacts completely. And when it does so, it converts HA into A minus. And that's what's going on between the initial point before you start and the equivalence point when the pH goes rocketing up at the on the right-hand side. That whole region in between there, as the titration proceeds, you're slowly converting HA into A minus through the addition of OH minus. Okay, that region then, you've got it partially converted, so you have present some HA and some A minus in differing proportions. As you go across, it makes more and more A minus and less HA. But you have both present, a conjugate acid-base pair, both present in significant amounts, and that meets our definition of a buffer. Okay, so it's very convenient through there. Because we can use the Henderson-Hasselbalch equation, and that whole region is called the buffer region. When you're titrating something weak, a weak acid, and conversely also if you're titrating a weak base with a strong acid, that initial portion between the start of the titration and the equivalence point is called the buffer region. So we'll learn how to handle calculation in there. Basically, all you have to do is figure out how many moles of each do you have, how many moles of HA and how many moles of A minus, and put it in the Henderson-Hasselbalch equation. Then, when you get to the equivalence point, at that point, all, or essentially all of the HA has been converted to A minus. And so what you have at that point, it's a salt solution, but it's not a neutral salt. Remember, A minus is a weak base. It's the conjugate base of a weak acid and is therefore itself a weak base. So you have a salt at the equivalence point, but it's a basic salt. If you start with a weak acid, then at the equivalence point, you have a basic salt solution. And we know how to calculate those as well. But the only thing is that it's the same number of moles, right? All the HA got converted to A minus, so the number of moles we know, but the volume has increased. You got to be careful about that. The volume has increased, so those same number of moles are in a different volume. That's why Harris has F prime. The formal concentration is different than the other F because the volume has increased. Then lastly, beyond the equivalence point, At that point, or in that region, the OH minus just dominates. Okay, what you have to figure out is how much OH minus have I added in excess of that required to reach the equivalence point. So you know how much you needed to get to the equivalence point, or you figure it out, and all of that reacts. All the OH minus that you added to get to the equivalence point reacts, and it's gone. Okay. Beyond the equivalence point, you continue to add OH minus, but it's got nothing to react with. So you just have OH minus in solution. You have to calculate how much excess OH minus have you added at any given point, and divide by, again, the total volume of the solution. Don't forget the total volume of the solution, which at that point would be the volume you started with before you started the titration, the volume required to get to the equivalence point, and whatever excess you're considering. So we're going to do each of those types of calculations in this video. So here's the question, okay? A half a gram of benzoic acid is dissolved in 100 milliliters of water, and it's going to be titrated with 0.135 molar KOH, potassium hydroxide, okay? That's the problem. And it gives the molar mass of the benzoic acid, and it gives Ka for the benzoic acid. Also calculated pKa for you. Okay, so we've got those all set up. And then we're going to do a whole series of calculations and peg this weak acid titration with a strong base. So first, what's the initial pH? As I said, that's a weak acid problem. What volume of titrant is required to reach the equivalence point? What is the pH after 11 milliliters have been added? In this case, that will turn out to be less than is needed to get to the equivalence point, and it'll be in that buffer region. Then there's a special point halfway to the equivalence point. We'll see what's going on there. And then the equivalence point itself. At that point, we'll have a solution of potassium benzoate, the salt of benzoic acid, and it is a basic salt, so we can figure that out. And then go 5 milliliters beyond the equivalence point and see what the pH is there. That's where OH minus is dominating the situation. You just have to calculate the concentration of OH minus. So anyway, number one, or A, initial pH. So this is just a weak acid problem. We get the number of moles of benzoic acid. It's a half a gram divided by the molar mass, 1.22 or 122.12, and it's 4.094 times 10 to the minus 3 moles of benzoic acid. I'm also giving it in millimoles because that'll be helpful later on. But the molarity is just that number of moles divided by 0.1 liters because we had 100 milliliters given. And that turns out to be 0.0409 moles per liter. So in these weak acid problems, recall that it's simply the square root of Ka times the formal concentration. And when we do that, we get 1.631 times 10 to the minus 3 molar, and take the negative base 10 log of that, and you have the pH, 2.79. We do have inherent in solving the problem that way is the x is small approximation. You have to check that x really is small. Divide that 1.63 times 10 to the minus 3, that's the x. And divide it by the original the molarity of the benzoic acid, the 0.0409, and it turns out to be about 4%. So it's okay. Next, the volume of titrant required to reach the equivalence point. We just calculated that the amount of benzoic acid is 4.094 millimoles. And so we need that same number of moles of OH minus to react with it. Okay, so we need 4.094 times 10 to the minus 3 moles of KOH, or OH minus, and the concentration of the OH minus was given as 0.0135 moles per liter. So that's going to mean we need 0.0303 liters, which is 30.3 milliliters. So that's where our equivalence point will be. That's when you've added enough base to react 1-to-1 with each mole of the benzoic acid, 30.3 milliliters. Now, the interesting part, pH after 11.0 milliliters of titrant have been added, okay? As the OH is added, it reacts with benzoic acid to produce benzoate. That's what's happening throughout the whole region in between the start of the titration and the equivalence point. OH minus is reacting with benzoic acid to produce benzoate. Okay. Throughout that region, they're both present in differing amounts. And we just need here to figure out how many moles of each benzoic acid and benzoate you have at the point that we're asked, the 11.0 milliliters. So 11.0 milliliters turns out to correspond to 1.485 millimoles. There's the calculation there. You just take that number of liters and multiply it by the molarity of the KOH. And so it's 1.485 millimoles. Okay. Originally, there were 4.094 millimoles of benzoic acid. All the OH minus is going to find a benzoic acid molecule and react with it and turn it into benzoate. So we can make a little table of what's happening here. You have benzoic acid plus OH minus makes water and benzoate. Before the addition, you have just essentially benzoic acid, 4.094 millimoles. And I'm just working in millimoles because there's no need to multiply the whole table by 10 to the minus 3. So initially there's no OH and very little of the benzoate. We add OH minus, the 1.485 millimoles we calculated above. Okay, each of those OH minus ions is going to attack a benzoic acid molecule and turn it into benzoate. So I'm going to subtract 1.485 from 4.094. I get 2.609, and also produce 1.485 millimoles of the benzoate. So that's the situation after we've added that amount of OH minus. Okay, we have 2.609 millimoles of the benzoic acid and 1.485 millimoles of the benzoate. And we can take that and put it directly into the Henderson-Hasselbalch equation. The base is the benzoate, 1.485, and the acid is the benzoic acid, 2.609. Take the ratio and the log. The 4.187 was given in the problem, that's the pKa. Then you calculate it out, and it's 3.94 for the pH after 11 milliliters of KOH have been added. The pH halfway to the equivalence point. Well, you see what's happened here. If you're halfway to the equivalence point, that means half of the benzoic acid has been converted to benzoate. Well, that means that the concentration of the benzoic acid and the benzoate are equal. And if they're equal, that means that the argument of the log in the Henderson-Hasselbalch equation, where you have base over acid, which in this case would be benzoate over benzoic acid, well, those are equal. So the argument would be 1. The log of 1 is 0. So it's worth remembering that halfway to the equivalence point is a special place where the pH is equal to the pKa, 4.19. You can just write it down. Now, the equivalence point itself. At this point, you have a salt solution. You started with weak acid, benzoic acid, and treated it with potassium hydroxide. So now you have a solution of potassium benzoate. But benzoate is the conjugate base of the weak acid, benzoic acid. It is therefore a weak base, and this is a basic salt. Potassium benzoate solutions are basic, okay? And furthermore, this solution is not any different than the solution you would obtain by dissolving the sodium benzoate. You could buy it in the store and dissolve the same number of moles in the same amount of water. You would have this exact same solution. So there's nothing magical about titrations producing this salt solution. It's the same salt solution you would get by dissolving potassium benzoate. Okay, the volume. You have to keep track of the volume here, right? So it was 100 milliliters when we started the titration. We took 30.3 milliliters to get to the equivalence point. So now you have 130.3 milliliters. The number of moles of benzoate is the same as what we started with in benzoic acid. In other words, all the benzoic acid got converted to benzoate, or you can figure that, and so you have 4.094 times 10 to the minus 3 moles of benzoate in 0.1303 liters of solution, and that makes for a 0.0314 molar solution of potassium benzoate. Okay, and we know how to do those calculations. The concentration of OH minus is just the square root of Kb. You have to remember you need Kb here times the molarity of the base. We know the molarity of the base. Kb is Kw over Ka, so put that in. You wind up with 2.19 times 10 to the minus 6 molar OH minus. Not very strongly basic, but you take the negative base 10 log of that, you have 5.66 times for the POH, and the pH is 8.34, okay? So that is worth remembering. When you start the titration with a weak acid, by the time you get to the equivalence point, you have a weak base. You have a basic salt and the solution is basic. You can see this solution at the equivalence point has a pH higher than 7. It's a basic solution. Now you probably remember that when we looked at titrating a strong acid with a strong base, when you get to the equivalence point you have a neutral salt and the pH is just 7, okay? If you see a titration curve that starts low, like this one did, so you're titrating an acid, but when you get to the equivalence point, the pH is higher than 7, you know that was a weak acid because it produced a weak base at the equivalence point. So yeah, you should be able to check in your mind that you get a basic, when you're doing a weak acid, you should get a basic solution at the equivalence point. Then lastly, want to look at beyond the equivalence point. Okay, so 5 milliliters beyond the equivalence point. This part, honestly, is just the same as when you're doing a strong acid titrated with a strong base. What you figure is OH minus added up until the equivalence point reacts. It's gone, okay? Then beyond the equivalence point, you add more OH minus, it has nothing to react with. So it's still swimming about. You have to figure out how much OH minus have you added beyond the equivalence point, how many moles, and then you have to figure the total volume, right? And people forget that, you know, they want to, it's like 100 milliliters to start, 30.3 milliliters to get to the equivalence point, and then this problem says 5 milliliters beyond that. So now we have 135.3, and it's just a matter of taking the number of moles of excess OH minus which we figured out, 5 milliliters times 0.135 moles per liter gives you this 6.75 times 10 to the minus 4 moles of OH minus. It's in 135.3 milliliters. You can figure out the molarity. Take the negative base 10 log, 2.30 for the pOH. The pH is now rather high, 11.7, because you have this strong base swimming about. So that is really the extent of it. You can do a number of other points for practice within this same problem. Practice using the Henderson-Hasselbalch equation, but we can calculate the pH at any point in these titration curves. It's also interesting exercise to consider the titration of a weak base with a strong acid. Maybe titrate some amine or something like that with HCl. In that case, instead of the titration curve starting out low and moving quickly high at the equivalence point and finishing with a basic solution, it's the other way around. You start with a high pH and go to a low pH. If you're titrating a weak acid with now if you're titrating a weak base with a strong acid, you have a basic solution to start, but you wind up with an acidic salt when you get to the equivalence point. So maybe we'll do one like that in a future video. But this is enough to get you started doing these kinds of problems, and it's just a matter of systematically taking into account all the volumes and so on. And the Henderson-Hasselbalch equation actually makes this easier than strong titration. Anyway, more to come.